Hey guys, I have your notes pulled up for section 11.3 day 2, and this is just kind of let's kind of refamiliarize yourself with polar curves. Let's watch how they're graphed and things like that. So I have your notes here, but I'm really not gonna use your notes. I'm not gonna write on your notes. I've got some writing on the board. If you want to copy it down, you can. If you want to just screenshot it and keep it for reference later. But I think really everything that I'm going to show you, it'll make sense to you, and you'll have it from now on. I don't think you'll need to write it down. Anyway, so basically, just what I'd like you to do is look at the different types of curves, functions, polar functions. Look at the different types there are, and look at what type of equation creates that shape of a graph. So look at what creates a circle, look at what creates a rose curve, what type of equation creates a rose curve. And these are French words, so I'm probably going to butcher them. So I think this is a limaçon and whatever. Not even going to try. And also notice too, not only the equation that creates that graph, but how long it takes to create that graph. For example, when you have a constant, in order to create this one complete graph, it's going to take a rotation of 2 pi to create that. If your equation looks like this, you're going to create a circle that touches the origin, and it only takes like half of a revolution to create this entire circle. And same here. So as you're looking at these, I strongly encourage you to play around with a few of them, take out your graphing calculator, graph them, set your window. Set your window so that from 0 to pi, so you can see that it makes one complete rose curve, given that much time. It's not time, it's an angle, I don't know what to call it. What happens if you put 2 pi in? And then, so I want you to see what's going to happen is it's going to graph the whole curve, and then your calculator at the top is going to be saying, I'm still working, I'm still working, I'm still working, and you'll see this get just a little bit darker. It's going to go back and like repeat itself. Now, you're going to need your graphing calculators today because I'm going to show you how to do some stuff on your graphing calculator. So if you need to pause the video and go grab that, do it. Alrighty, hopefully you can see the board well. So I want to kind of revisit polar coordinates and rectangular coordinates and what R is. So when you have rectangular coordinates, you've got an X value and a Y value to create an ordered pair. We often call the hypotenuse R, and we find R by doing the Pythagorean theorem. When you make a polar graph, your coordinates are polar coordinates. This is, we call it the radius, and we say radius, comma, theta. This means how far out am I going to go from the origin, and then this says how much of an angle of rotation am I going to have. And then we create this ordered pair. This is a length measurement. This is an angle measurement. Okay, and then a lot of times you see graphs that look like this, where there's like a circle. It's common. And you think, oh, R is just the radius of that circle. That's what R represents, the radius of the circle. If your circle's at the origin, that can be true. But when you have a polar graph, when we really get into polar graphing, R does not represent the radius of a circle just because I have a circle on a graph. So If your circle center is at the origin, yes, R can represent the radius of the circle. What if your circle is not centered at the origin? Now what does R represent? So here's what I'd like you to do. I'd like to shift your thinking. R doesn't necessarily, when we're polar graphing, R doesn't necessarily represent the radius of the circle. R represents the distance from the origin to our function or to our point on a function. R represents the distance from the origin to the function. From the origin to the function. So, what I've got graphed here on the board is one of this type of equation. So I graphed R equals 1 sine theta. I would like for us to set up our calculators together to look at this. So, a couple things you're going to need to do on your graphing calculator. Go to mode. I think you're going to have to make 2 changes because so far we've looked at parametric functions and we've looked at, you've been working with vectors, so you've been working in degrees. So I want you to change 2 things. Go down, go back to radians, out of degrees, go back to radians, and where you changed it from function to parametric, I want you to go over one more and change it to polar. Okay? And then we're going to go, you're going to hit your y equals, and it'll give you R instead. It's going to allow you to type an equation for R in terms of theta. A lot of times you type a y equals equation in terms of x. We're going to type in a polar equation in terms of theta. So go ahead in your y equals and type in sine theta. And you can set up your window. So what's going to happen is we're going to get one complete circle from 0 to pi. So go to your window. Your theta min needs to be 0. Your theta max needs to be pi. You can just type the pi symbol. Your theta step, I've got mine small enough to where I can like really see it graph nice, kind of nice and slowly. Let's do you can do an x min at -1, an x max at 1, and then whatever. Go to at least 1 on your y-axis. Set up your window, and in fact, go ahead and graph it. So when you hit graph, you're going to see that it starts here, draws the circle this way, and it stops when it hits pi. When theta is pi. Okay, now, I would also like you to get these values in your table. So I'm going to show you how to set up your table, and this should be really helpful from now on when you're graphing polar coordinates and you want to see what's going on in your graph. This is going to be really helpful. So here we go. Ready? You're going to go to table set. I want you to start your table at 0. Delta table. So this is asking, what do you want to count by? This is important. From 0 to pi over 6, and pi over 6 to pi over 4, and pi over 4 to pi over 3, that is not a constant change. It's not the same every single time. But I want all of them to show up for you in your table. So, solution. Count by 12s. So make your delta table pi divided by 12. And set your independent to auto, and this will automatically populate your table. And then hit table. Once you do that, your table is going to be considerably longer than mine. And here's why. You're counting by 12s. I left out some polar coordinates. So I left out 1 pi over 12. I didn't want to look at it. That's not a common angle. I did want to look at 2 pi over 12 and 3 pi over 12 and 4 pi over 12. I did not want to look at 5 pi over 12, so I left it out. 6 pi over 12. I wanted that one. I wrote it down. 7 pi over 12, I skipped it. 8 pi over 12, 9 pi over 12, 10 pi over 12, 11 pi over 12 I ignored, and 12 pi over 12. I wrote that one down. And I know yours are in decimal form. No big deal. Y'all are so smart. Pi over 6 is like 3-ish over 6. That's about half. 3-ish over 4, it's about 0.75. 3.14 over 3, that's just over 1. You get it. Okay? And then you've got your R values over here that correspond with your theta values. So here's what's going on in this table. All of these points are graphed in this order. So when the calculator drew your graph, it said, I'm going to start here, and I'm going to, now I know it drew all the points in between, but let's say it focused on these 8 points. So I'm going to start at 0, 0, and then I'm going to draw from here. I'm going to go out a radius of a half, and I'm going to open up an angle of pi over 6, and got that. So the distance from here to here is a half. That's R. And then it does the next one. It says I'm going to go out a distance of 0.7, and I'm going to open an angle rotation of pi over 4. So this distance right here is approximately 0.7. And then it went out 0.8 and opened up a bigger angle. And then it went out all the way to 1 and opened up an angle of pi over 2. And that's where I get this measurement is 1. And then for over here, it went a positive radius, so it's this direction, 0.8, and then it opened up an angle of 2 pi over 3. So this distance is 0.8, and so on until it comes back down here, and now it says don't go anywhere, but we've had a rotation of pi. So R, once again, R represents the distance from the origin to your function. All right, that's it. I encourage you to kind of go through the notes, play around, graph a few. When you're graphing some rose curves, change the A value out front, change the N value in front of theta, and see what that does. Change your window from 0 to pi or 0 to 2 pi. See what happens. Challenge yourself and say, okay, you know what? I'm going to graph this rose curve, but I'm just going to graph one petal. I'm going to see if I can figure out how to make my calculator graph one petal. Okay? Oh, one more thing I wanted to tell you. When you have a polar graph and your radius is a constant, that means I'm going to run out of room here. That means your angle can be anything, and that's what gets you a circle centered at the origin. If your radius is a constant, your degree can be anything. What if theta is a constant? Right? It's kind of like comparing, what if I graph x equals 2 versus the graph of y equals 2? So it's kind of like that. What if theta is a constant? This time, it means theta is a constant. R can be anything, but theta is a constant angle. Here's what that means. If R is positive and we have this theta measurement, R can be any length along here. Or R could be negative, and I could have a theta measurement. So if R is negative, think about same distance, come out here, same theta measurement. R can be anything. I can come out -1 and do a theta rotation, the same as up here. R could be -2 theta rotation, same as up here, and so on. So if R is a constant, this is the type of graph we're looking at. If theta is a constant, it's just a line. That's pretty cool. All right, so kind of play around with those. Get used to how to maneuver around on your graphing calculator. You've got a quick My Math Lab that shouldn't take you too long. Enjoy.